What if I tell you that if you know how to calculate the shear force and bending moment at any given point along the length of this beam, you can calculate the slope and deflection also. Now, this may sound weird that how does calculating shear force relate to slope, and how does calculating bending moment relate to deflection? Yes, there is a connection, and the method through which we are going to establish this connection and also solve a problem of simply supported beam today is what is known as, or rather popularly known as, the conjugate beam method. This lecture is going to be very, very interesting. So I want all of you for the next 15 minutes to stay with me, to stick your eyes and focus. Okay, here we go. Conjugate beam method. Now, for all of you who don't know what is deflection, here is a very small demonstration. This is a beam. Okay, this red color line that you see, that's the longitudinal axis, and perpendicular to it we've got the loads. What will happen to the beam? Obviously it is going to bend. Okay, so this bend has been very exaggerated. If the beam bends like this, your life as an engineer, your career as an engineer would end. Okay, your beams should never flex this much. Anyway, so this is the initial position. Okay, very light, and this is the final position. If I were to explain as to what exactly deflection is, let's say this is before, the point was here, this is the point after applying the loads, and you can clearly see there is this vertical displacement. This vertical displacement is what is known as deflection. And so far there are two calculus based techniques that we've learned. One happens to be the double integration method. The second technique was the Macaulay method, which is an advancement on the double integration technique. And the third method, which was very popular, moment area method. The technique that we are going to learn today, the conjugate beam technique, is a subcategory of moment area method. Okay, so this is going to be very interesting. No calculus involved. The only skill that I expect from all of you is to know how shear forces and bending moments can be calculated. And one second, I have added the playlist for SF and BM calculation in the description. I've also added the playlist for the entire deflection of beam. So if you've got time, binge watch all of those lectures and sharpen your skills. SFBM calculation, sharpen your skills as to how you can apply the double integration technique, as to how you can apply the Macaulay method, the moment area method, to find the beam deflection. These things are very, very interesting. Okay, binge watch all of those lectures. Here we go. Conjugate beam method, sir. We are going to start with a relationship that I have established, that I had established in my lecture number 1 of deflection of beams playlist. Watch that lecture. Complete derivation is given in that video. Okay, it's a very important relationship. And if I were to simplify this, this is d2y over dx square is equal to bending moment m. Can be done. Okay, now if I start integrating this expression, what will happen? I'll get ei dy over dx. It will take me to slope. If I integrate this again, I'll get eiy. It will take me to deflection. That means integration of this very expression leads to slope and finally to deflection. However, if you differentiate it, you get an entirely different set of parameters. If you differentiate it, ei d3y over dx square will take you to the shear force. Okay, remember, shear force. If you differentiate moment, you get the shear force. If you differentiate this expression, you get the shear force. If you differentiate it again, what you get is the load. Okay, you differentiate this again, what you get is the load. So far, so good. But we still are not getting the point as to how you are relating shear force with the slope. Slope is a angle. What is that angle? Can it be seen? Yes, it can be seen. And bending moment, you are relating the bending moment to deflection. Deflection, let's say y, vertical displacement, isn't it? What is slope? First of all, let me clear this. Let's say you've got this very point on the beam. Okay, if you draw a tangent, let me do this again. If you draw a tangent like touch and go, what is this? That's a tangent. The angle that the tangent makes with the positive x-axis, this angle that it makes with the positive x-axis, let's say this is point C, this is known as the slope at point C along the length or on the beam. Okay, so this is going to be our objective today, to find the slope of the beam. Also, this vertical displacement, this over here is represented by YC. This is what you call the deflection at point C. Obviously, when you solve numericals, you'll be asked to find the slopes and deflection at different points on the beam. So you should be skilled enough. I'm sure you will be after watching this lecture to find the slopes and deflections. No problem. So far, so good. Okay, now let's develop the analogy as to how shear force is connected to slope and bending moment is connected to vertical displacement, that is deflection. And by the way, this conjugate beam method, this is a real beam. First of all, let me just clarify this. And an imaginary beam is something that we'll construct, we'll analyze, okay, we'll do the calculations. That imaginary beam is known as the conjugate beam. Let's develop the analogy, and let me pick instead, I think, this relationship, and let me pick one more, this relationship. Let me keep them side by side. Analogy number one for sort of connecting slope with the shear force. Here we go. Okay, watch this very carefully. What can we do to this? That we can write it as d by dx of dy by dx. Can we do this? Yes, sir. And what about dy over dx? What can you replace this with? Sir, dy by dx is nothing but the slope. Is that really true? If you watch, let's say this is our beam. And after applying some kind of load, let's say that load happens to be W. This is the new position of the beam. This becomes the new position of the beam. Again, I am exaggerating. Okay. So far, so good. Now let me make a point over here. And if I draw a tangent, again, the angle that this tangent makes with this positive x-axis is referred to as the slope, theta. Okay. If you watch carefully, since this is the tangent, this small dy, very small dx. Okay. And let me just zoom in. If this is theta, this also is theta, very small angle, right? Very, very small angle. So tan theta is essentially equal to dy over dx. So if theta is very, very small, okay, in that case, tan theta can be approximated as theta, and theta is equal to dy over dx, which is popularly known as slope. This is something that you have learned in trigonometry, you have learned in coordinate geometry, right? Now, let me replace this dy by dx by theta, and here we go. That's the relationship. So, again, the question is, how do we connect shear force with the slope? Here is the connection. Watch this. Load over to the RHS of a real beam. Okay. M over EI. You have the load diagram. Let me just write this as the load diagram. DIAG. Here, this is the M over EI diagram. What? Let's say you have constructed an imaginary beam with an M over EI diagram. Just listen to me. Listen to me. Everything will make sense. What we have been doing from the load diagram, we know how to calculate the shear force. Shear force values. At any point, we know how to do the calculation. We can take this section, or you can generally apply the method. In the same fashion, if you have the M over EI diagram, and if you know how to calculate the shear force value for the conjugate beam, what you will have finally is the slope for the real beam. That means if you have made the conjugate beam, if you have put the loading is in the form of M over EI, and you calculate the shear force value at any given point, that shear force value actually qualifies as the slope for the real beam. Okay, I am going to demonstrate this to you, that the shear force calculated for a conjugate beam qualifies as the slope for the real beam. Yes, that is true. This will happen. Okay, provided you have the M over EI diagram, provided you have the conjugate beam. Okay, it's very easy to make the conjugate beam. Don't worry, I'll give you all the notes. Okay, not to worry. Keep watching. Okay, so far so good. Now we come to the another analogy, which is for deflection. I'm going to be using one more relationship. This one, EI d2y by dx square is equal to M, and another one, EI d4y over dx power 4. If you forgot, this is what I am using. This and this, obviously. Okay, here we go again. Analogy for deflection, and here we go. What's next, sir? Can I write it like this? d2 by dx4. This way. I've shifted EI over here. d2 by dx2 or dx square. This way. What can I replace this with? Sir, d2y by dx square. d2y by dx square is nothing but M over EI. Just do the replacement. Done. Now solve it, or rather simplify it. What will happen is EI and EI will be out of the differential and it will cancel each other out. What remains is just this much. Okay, so what I essentially I'm trying to convey is, if you have the real loading, if you have the real diagram, the loading diagram, and you try to calculate the bending moment value at any point along the beam, you are calculating the bending moment only for a real beam. However, if you have the M over EI diagram, that means if you have drawn the conjugate beam with M over EI as the loading, this M over EI is now the loading for the conjugate beam. And again, if you try to calculate the bending moment value, yes, you are calculating the bending moment value for the conjugate beam, but this actually qualifies as the deflection or the vertical displacement for a real beam. Okay, let me just summarize this. Here we go. M over EI diagram, W diagram. M over EI as the load in the conjugate beam, W as the load in the real beam. Okay, what do they signify? From here, if you find the shear force, you are going to get the shear force. But here, if you try to calculate the shear force value, what you get is the slope for the real beam. There is a connection. In the same fashion, if you have the real load and if you want to get the bending moment value, you can do this. By calculating the bending moment value, you are going to get the bending moment only. However, when you talk about the conjugate beam, when it is loaded with M over EI, if you try to calculate the bending moment value, what you are indirectly trying to calculate is the deflection for the real beam. Okay, so this is slope. Let me summarize this again. Conjugate beam, what is the loading? M over EI is the loading. Shear force for the conjugate beam is the slope for the real beam. Bending moment for the conjugate beam is the deflection for the real beam. So this is the crux. And now let's move forward and let's discuss a few more points which are very important. Okay, here we go. And this is the sort of integral form. If you just take dx to the right, do the integral, this is how it would look, right? Again, the same thing. M over EI will get you to the slope. M over EI will get you to the deflection, provided this calculation has been done as if you are calculating the shear force, and this calculation has been done as if you are calculating the bending moment. So I would suggest all of you to keep on taking the pictures in between or keep on making the notes. Very, very important. Here we go. Real beam versus conjugate beam. Watch this. And I'm assuming that you know how to make the shear force diagram and the bending moment diagram. Okay. So 10 kilonewton load is acting downwards centrally. So the load is going to be shared between support at A and B. This is going to be 5. This is also going to be same 5. And the shear force diagram would look something like this. the bending moment would be maximum at this central point. So 5 force multiplied by this perpendicular distance, 5 into 5 is 25, so that's 25. Okay, and this is how it is uniformly varying from one end to the center, from other end to the center. That's it. Very easy. So far so good, no issues. If you have this as the loading diagram, and let's say I ask you to find the slope and deflection, slope at these endpoints and the deflection at this center, how would you make the conjugate beam in such a case? So it's very easy. This is the M diagram. For a conjugate beam, I have been stressing on this point repeatedly that you need to make the M over EI diagram. What? M over EI. So take this value, take this diagram onto this beam, and this is how it is going to look. Okay, so this is value M, which has been divided by EI. This is the M over EI diagram. Since all of these are positive values, here the value is positive, here the value is positive, that's why the arrows are pointed in the upward direction. So far so good. Okay, now point number 2, please note, bending moment diagram from the loading diagram. Bending moment diagram from the loading diagram provides the bending moment at any section. You know this. Let's say you are making bending moment at this very point. This is the value of that bending moment. It is a positive value, right? Real beam, you are calculating the bending moment, you get the bending moment. But for a conjugate beam, when you are calculating the bending moment, you actually get, let's say at this very point. For a conjugate beam, when you make the bending moment diagram, and let's say you've got the bending moment value at this very point, this actually gives you the value of deflection. Let's say this is point C, so this has become your deflection, right? Bending moment diagram from the loading diagram provides the deflection y at any section. All right, the next point, here we go. Shear force diagram provides the shear force at any section. Yes, here it is. This is the value of shear force, negative value over here. However, as far as a conjugate beam is concerned, if you find the shear force, let's say if you find the shear force over here, what you get is the slope over here. That means this angle is what you would be getting from a conjugate beam. If you can find this shear force here, what you actually get is the slope. That means theta, let's say at point C, this is what you get. So now I think we have established this connection beautifully. And now please remember one more thing, the boundary conditions have to stay same. And in today's lecture, I am discussing only the simply supported beam. In the upcoming lectures, I'll be also discussing the cantilever beams and beams where there is an internal support. Okay, those things, those complicated stuff will also be discussed. Need not worry. Bending moment at the supports of a simply supported beam is 0. Yes, at A and B, these are the supports. You can clearly see the bending moment is 0. Bending moment is associated with what? Sir, bending moment is associated with deflection. So here, the same condition must suffice. It means here also the bending moments, if you try to make the bending moment for this conjugate beam, here also it should be 0. Yes, it will be 0. The loading is a bit different, yet you will realize this, that the bending moment is also 0. So both the boundary conditions are matching, no problem. No need to make any alteration in the beam. The real beam is going to look exactly like the conjugate beam. The only difference being that this moment diagram will be divided by EI. Okay, and then we are going to make that stuff. Even now I can understand this may sound a bit weird, but everything is going to fall into place. The next point, shear force at the supports of a simply supported beam exists. Shear force is existing. Okay, slope at the support exists. If these two conditions are matching, then no problem. No need to make any alterations. Once again, no need to make any alterations. Okay, here also if you try to calculate, there is going to be some non-zero value of shear force at this point and some non-zero value of shear force at this point. Why? Because there is going to be some slope over here. This is a negative slope. There is going to be some slope over here also. This is going to be a positive slope. Clock, anti-clock, positive, clock, negative. I hope you got the point. Now it is a time to move towards solving the problem. Example number 1. Here we go. What is this? So looks like a simply supported beam. Yes, it is. Okay, central load W, and these are the supports, hinge and a roller. Find the expressions for central deflection at the center, and the slope at the ends. What you basically need to work out is, let me just draw this to you. Let's say that the beam deflects in this fashion. What you need to work out is the slope at A, the slope at B, and the displacement over here, or the deflection. Okay, let's call this point as point C. So we need to find YC. You need to find theta B, which you already know is going to be positive. Angle has been measured anti-clockwise. That's the reason. Again, positive x-axis. This angle is what you need to work out, theta A. Let me zoom into this. I think the objective is clear now. What is going to be our first step? Sir, the first step is to make the conjugate beam. So, okay, so conjugate beam, we know the loading is M over EI. So you need to know the moment values at all the points. Okay, so better to make a bending moment diagram for this real beam. Again, if the load is acting in the downward direction, these are the reactions, RA and RB, right? If you watch carefully, this load is equally distributed. This is W over 2. This again is W over 2. How can we calculate the bending moment? It's very simple. Let's say you want the bending moment at this very point. Okay, the load is acting in the upward direction. This would have a tendency to bend the beam in this fashion. This is like half of a smiley face. If you complete it, this is what is known as a sagging case. What? Sagging case, and the bending moment is positive. So W by 2 happens to be a force. This is that line of action multiplied by a perpendicular dropped from C. Here is that perpendicular. Okay, so force multiplied by perpendicular. W by 2 is the force multiplied by this perpendicular, that's L by 2. So I'm also recapitulating your basics. W, L by 4 happens to be the bending moment over here. And as we move from C to either A or B, the bending moment values are going to keep on decreasing. Okay, because L is going to decrease. L by 2 will decrease to 0, let's say. Here it is. This is a triangular variation. Now, as I told you, if I were to make a conjugate beam, since this is a simply supported case, no need to make any alterations. The beam will stay the same. The loading will change. This bending moment diagram BMD will be put up or put on to a conjugate beam in this fashion. That's a conjugate beam. Since you saw this, all these values are positive, isn't it? That's why the arrows are pointing here in the upward direction. That's a conjugate beam for you. Now, you just need to find the shear force for the conjugate beam. You are going to get the slopes. You just need to find the bending moment. At this very point of the beam, you can get to the deflection. How do we do that? Statics. Okay, make the free body diagram. And how do you deal with this triangularly varying load? I'm going to let you know, don't worry. It's already 23 minutes. I promised that I would finish the lecture in 15 minutes. I'm really sorry. Okay. So let me remove the supports. And obviously, if the load is acting in the upward direction, the reactions will be downwards. What do you do now? Sir, RA is downwards. So our sign convention is upward, positive. Downwards, negative. Okay. So minus RA, minus RB. Done. Okay. Minus RA, minus RB. What now? What about this load? Whenever you're dealing with a triangularly varying load, please remember that if I were to replace this entirely triangularly varying load with a single point load, if I were to replace this with a single point load like this, that load would be acting at the center. Yes, that is true. But what would the magnitude be? The magnitude will be equal to the area of the triangle. Half of base. Base is L by 2 plus L by 2. That's L into the height. The height happens to be WL over 4EI. WL over 4EI. Okay. Once again, if I were to replace this entire triangularly varying load with a single point load, it would be this much. This much. Okay, let me write it over here. Done. Easy. Now, let me rewrite this in a better way. And you can clearly see, since the entire distributed load is symmetric about the central point C, therefore RA and RB will be equal. Divided by 2, you will get the value as WL square upon 16 EI. I hope this is clear to everyone. Is it? All right. You've got the reactions. Let me replace this RA with WL square by 16 EI and also RB. Done. Okay. The equations of statics have been applied to calculate the reactions at end supports. Now, once you calculate the shear force, you get the slope. Where do we want the slope? Sir, we want the slope at B and at A. How would the slope look like? Sir, the beam would bend in this fashion. The slope at B would be this fashion. Slope at A would be something like this. That means this is going to be slope at A and this is going to be the slope at B. Wonderful. Now, you need to take a section. What? You need to take a section. Take a section somewhere here. Okay. Whenever you take the section from the right, shear force upwards, bending moment clockwise. Okay, I have taken this much section of the beam. That is why only this much portion of the triangularly varying load has been drawn. Section from the right at a distance x. Can you express the bending moment and shear force in terms of x? Yes, you can. Okay, with a bit of common sense, let me illustrate that to you. First of all, please tell me how much this height is. Sir, this height is, it's very simple. It's WL over 4EI. Okay, very well. How much is this height? Sir, we don't know. Can you calculate? Yes, we can. What we'll do is, let me simply write P over here. Let's say our objective right now is to find this value of P in terms of X. Can we do that? Yes, we can. If you watch carefully, these two triangles, what is the property they share? Sir, these two triangles, they are appearing similar. Yes, they are similar. Then the ratio of the sides would be same. Okay. Perpendicular upon perpendicular is equal to base upon base, and that is the logic which we'll be using. Okay. So WL upon 4EI divided by P, or you can also say P divided by this much. Okay. And X divided by L by 2. Just try to solve this. You're going to get P in terms of X. This is what we wanted. Done. No problem. Okay. So you've got P. Now can you calculate this shear force? Yes, we can. If you watch, this shear force is acting in the upward direction, positive. Okay. And this triangularly varying load is actually acting in the upward direction. So that will also be positive. What is the magnitude going to be? That will be a bit challenging. Take a look. Here I'm writing Vx is upwards. That's why positive. Okay. And as far as this triangularly varying load is concerned, let me zoom into this. Vx is positive. How did I get to this result? Half of x into this much. So half of base, that is x into height. This is P. P is equal to, sir, P is equal to Wx upon 2EI. And here it is Wx upon 2EI. Okay. Now you got the point, right? And this triangularly varying load, let's say this entire green color load has been, if I can replace it with a single point load, it would look something like this. That is W how much? Wx square upon 4EI. Wx square upon 4EI. Let me repeat that once again. If I am replacing this green color load, triangularly varying load with a point load, it has to be this much. Okay. And that point load is acting at a distance of x by 3. These are the properties of centroids. You must know this, right? X by 3 from over here. Okay. Anyway, this is done. Now one more thing. This WL square upon 16EI is acting in the downward direction, negative. It is equal to 0. And now you just try to simplify this. Keep Vx to the LHS and everything else to the RHS. This is what you get. Okay, so far so good. Now, let's say you want the slope or you want the shear force of the conjugate beam. Okay, at B. So put x is equal to 0. If you want the same value at C, you are going to put x is equal to L by 2. Am I right? Yes. So put x is equal to 0. You are going to get shear force at B. Just put the value. Okay, x is equal to 0 over here. What you're left with is this first term, WL square upon 16EI. It may be called as the shear force for the conjugate beam, but this will qualify as the slope for the real beam. Okay, what is shear force for the conjugate beam is slope for the real beam. I hope you have got this by now. Secondly, if I put the value of x as L by 2, just put this value as L by 2, WL square upon 16EI minus W by 4EI into L by 2 square. You'll realize that the slope happens to be 0, and it's very obvious. Yes, the slope is going to be 0. Take a look. Here it is. You want the slope over here. If you draw a tangent, is this tangent, green color tangent, making any angle with the positive x-axis? No, sir, it is not making any angle. When you don't make any angle, that is actually 0 degrees, right? I hope you got the point. Okay, slope done. Slope at the ends done. Okay, in the same fashion, you can take one more section over here, although you don't have to do it, and this slope is working out as positive. The reason being very simple. If you draw a tangent like this, that makes an angle of theta. This is measured anti-clockwise with respect to positive x-axis. That's why it has worked out positive. You can see this. Okay, now coming to the part of bending moment. When you calculate the bending moment in a conjugate beam, you get the deflection for the real beam. Here it is. Take a look. Please let me rub this also. Okay, take a look. If you don't know, this is my sign convention. Clockwise is negative, anti-clockwise positive, and in most of the foreign author books you'll see them following this sign convention, be it R.C. Hibla, be it Peer and Johnson. Okay, all right, just a sec. Okay, now it's stable. So bending moment is acting clockwise at this very section, so this is going to be negative mx. What else? As I told you before, I am replacing this triangularly varying load with this point load, Wx square upon 4EI. That is the force. This force multiplied by the perpendicular distance. Sir, where is that perpendicular distance? Can you show this again? Here it is. This is that perpendicular distance. Force and distance. How much is this distance? Sir, this is actually x over 3. Always measurement has to be done from the right angle. X by 3 from the right angle. Okay, x by 3. So very easy. Wx square upon 4EI multiplied by x by 3, and let me write it. And watch carefully. This is making an anti-clockwise sense at this section. If you keep your thumb over here, and move this finger, this finger I'm talking about. Just do it. The movement is anti-clockwise, and that's why we've done this positive sign. Okay, and as far as this force is concerned, that is the force, and this is the perpendicular distance. How much is this distance? So this is known to, that's x. So WL square by 16EI into x. This is making a clockwise movement, negative sign. Keep mx to one side of the equation and the rest to the other. You have the bending moment in terms of x. Now, when you plug in the value of, what do you need? You need the central deflection. That means x is going to be equal to L by 2. Just put the value of x as L by 2. You are going to get the central deflection. Just put it. It's very simple. Solve for it. This is what you get. Okay. That is the deflection. And you can clearly see you got a negative value. Again, the reason being very simple. Where should I make it? The reason being very simple. I'm better with pen and paper than this tablet. Okay. Here you got the deflection. This is what you've got. Why? See, you also have got this slope. Theta b. The answer was positive. Okay. And I want all of you to calculate the slope at A, which I'm sure will work out negatively. Okay. If you take a section, let me assume that you have taken section from the right hand side. Your section would be looking something of this sort. This way and this way. This is how it would look. Obviously, the arrows will be in the upward direction. Just try to do it. I'm sure when you apply x is equal to L by 2, slope is going to be 0. And when you apply x is equal to L, there is going to be some value of slope, right? Slope at A, and it is going to be a negative value. All right, so let me just show you the answers again. And where is it? Yeah. So yes, that was all from my side for today. A problem based on simply supported beams slope and deflection calculation using the conjugate beam method. With a little practice, I'm sure that you can save a lot of time. So guys, yes, that was all from my side for today. And if you believe that this content has added value to your knowledge of mechanics of solids, then feel free to subscribe to the channel and also share it with your friends and classmates so that they can also benefit. This is Manas Patnaik signing off. Take care and have a nice day.